Welcome to our section on how forces act on water in the soil. And this, in my opinion, is going to be very life-changing for you in the way that you think about how water moves around in the soil and how plants get water. One thing that you probably do know about is gravitational water. Gravitational water is water that moves down through the soil profile. So we talked about runoff, or we're going to talk about runoff in some later things. Not that water, but the water that comes down. So most everybody understands that. Adhesion water is the water that's held to soil. And it's held to soil, it can be held to soil very strongly. And in that case, it can be held so strongly that plants can't even get that water. And we'll talk about that as we move forward in this section. And then cohesion water. And cohesion water is the water that beads on your car. After you wax your car, the surface becomes less permeable to water. It becomes more hydrophobic. So the water-to-water bond, remember water's a charged molecule. There's the hydrogen plus side, and then there's the OH minus side, and the minuses and pluses will line up and hold each other. But that's a weak bond, and that's a bond that usually the plants can break when they take up water. So plants use this loosely held cohesion water. So one of the things you probably have never thought of is water moving up in the soil. And most water is moving up. These adhesion and cohesion forces, as water is taken off the top of the surface by evapotranspiration, water will move up to fill those spaces. And here's a pretty good example. We've got our soil. We've got the air here, and the air is pulling moisture off the top, and we oftentimes get a layer that's at the top that's dry. And then in these pore spaces is water, and in different amounts of water, and sometimes they'll be full. Gravity will pull it down further, and we're going to show some pretty good pictures of that as we move forward. But I want you to think of the soil as a three-dimensional space and realize the fact that water can move in all directions in that three-dimensional space. Water moving in that three-dimensional space is always going to try to go to its lowest energy state. And all things try to go to their lowest energy state. Rocks will fall, water flows downhill. We're always going from positive energy to negative energy, going to the lowest water potential in the soil. The lower the water potential, the stronger it is held. And here's our diagram we're going to show many times through the course of this lecture. And you need to understand that field capacity is the point where the soil is at negative 1/3 bar. So all water, gravitational water, is going to be pulled down. That will not be available. So any water at a matrix potential higher than negative 1/3 bar is not going to ever be available to the plant, because that's going to be moving down, and you need to understand that. The cohesion water from negative 1/3 bar, and a bar is about 30 pounds of pressure, so that's negative 30 pounds of pressure. So that's a suction, that's a tension. A vacuum could create these negative tensions, which hold water. But this water is going to be available for the plants. The cohesion water, that's the water-to-water water. And then the adhesion water, that's water that's held to the soil particle, because the soil particle is dry and it needs a layer of water around it. And that adhesion water, that at less than negative 31 bar, is not going to be available to the plant. And then right up next to the soil, if we were to dry it with an oven, we could remove the adhesion water, but only to a point. There'd probably still be a little bit of water around that soil particle that could be held up to minus 10,000 bar. So three forces we're going to talk about that act on water. Matrix potential, which is any negative potential. So things going from high to low potential, they're always going to go towards the lower side. It takes work to move it against that. So that would be a vacuum. We could pull against any negative matrix potential by creating a stronger negative potential somewhere else. So through matrix potential, water can move in all directions. Gravitational potential is going to be down, the gravitational forces of the Earth. And then another one that we haven't talked about but is going to become pretty important is osmotic potential. Osmotic potential is salt. So if we have salt in an area, it will draw water. This becomes very important in fertilization, because when plants die from over-fertilization, it's usually because of osmotic potential. It's usually because they run out of water. The other thing that's happening and why osmotic potential is going to be important is effluent water. And some of the brackish water or effluent water that's being used in the turf industry is going to add salts to the system and change the way water moves through the soil as salts accumulate at different places where they may accumulate either on the top or down. Water will move according to those osmotic potentials, and you need to be aware of those and understand what those salts do. So one thing you should be able to do is convert bar to PSI. So 1 bar is 14.5 PSI. So negative 15 bar, which is 217 pounds per square inch, pretty high PSI, is the maximum that any plant can pull water. And once the soil gets that dry, we can measure that. That's a pretty dry state for the soil to be in. The plants will reach what we call permanent wilting point. Once permanent wilting point is made, that's not temporary wilting point, that's permanent wilting point, plant's dead. So this hygroscopic water, that's water that's attached to the soil particle very strongly, and it can only be removed by oven drying. So anything between negative 1/3 bar, which would be a third of 14, which is a little bit over 4.5 PSI, to 217 PSI is available for the plant. And that's can be shown on this diagram. So this negative 15 bar is going to be about here. So there's even some cohesion water that's not going to be available for the plant. And the plant available water is going to be important. And plants have different strategies of getting water, and some of them include putting roots into more places, wider places, deeper places to try to get at the available cohesion water between negative 1/3 bar and negative 15 bar. So when we did our water calculations, water retention, our moisture percentage, we did a conversion where we converted that to inches of water. And this is an interesting graph just for thinking about how different soils act and how sand changes the available water for plants. So this data is all in inches of water per foot of soil. So field capacity in a sandy soil is going to be 1.4 inches of water. In a sandy loam, we could have up to 2.5. A loam, 3.1. In a clay loam, we could have 3.7 inches per foot of water that's in the soil. That doesn't make it necessarily available. Permanent wilting point is going to be reached, so that would be the maximum, the minimum water in the soil at all times that's not available to the plant. And we can see that the highest amount of water taken up would be a silty loam. So when we subtract the permanent wilting point from the field capacity, we come up with the number of inches of water available to the plant at field capacity. And you can see a sand is going to be much lower, so a silt loam is going to have the most available water for a plant. So either ends of the spectrum, a clay is going to hold so much water, this 3.9, not available to the plant. This number actually increases as we go from coarse soil to fine soil. But this number goes up and then comes back down. So just a way for you to think about it, and you should spend some time and think about this to understand how soils affect plants, and particularly turf grass, sandy soils versus clay soils. So water is always moving through the soil. In a saturated flow situation where we have water on the surface that needs to go down, it's going to move rapidly through gravitational water. Unsaturated flow in all the other directions is a slower process, back up, and it's going to be inhibited by coarse soils. You can think about that. The micropores are going to be further away from each other. The water's not going to be as easily wicked through a coarse soil. And through gravel, it's probably not going to wick back up. So there's a different way to think. Again, think about the three-dimensional things that are going on in the soil. So unsaturated flow is pretty much all directions, saturated flow down. And here's a nice drawing to show you what they did is they put dye in these spots, and then this is water, a head, and the head of water is here. So this water is moving by gravitational flow down here, and it's also moving up through capillary action. And you can see from this point all the water moved through this way, up and down. So the water from this one irrigation trough in this soil is going to move in all directions. We can see the gravitational waterfront has reached here. So this is another important point. Soil's either at field capacity or dry. So this, if we stop the water here, this area of sand would not wet. The water would start to dry and water would move up by capillary action back to fill the drying from the surface. So this is a good way to think about how water moves through soil. So a little summary in words of how water moves in a soil. First, downward after a rain through gravitational water. Then up to evaporate or to transpire, evapotranspiration. And sideways from wet to dry areas. So that's one that we don't think about. Oftentimes on a golf course, particularly a putting green that's sloped, a lot of water is going to move sideways. It will wet and then move quickly down slopes, and then it can stack up at the front when soil layers change. So the three-dimensional sideways movement of water is something not often thought about, but is very important, particularly when hand watering or when irrigation is not as uniform as we would like it to be. So here's another example of that wetting front. A soil volume we can't half wet. And I really like this slide because it shows what a core hole does. If we have a core aerification hole that's filled with sand, a coarser material, all the way to the top, when we wet it, water moves down that core hole and fills the space. So it wets more completely, it decreases surface runoff and increases infiltration. If we have a core hole that's sealed at the top, which often happens if it caves in, we don't fill it all the way, and we get muck in there. This does not wet, so we can't wet this area. This core hole will not wet until the wetting front comes all the way behind here. Then water can get in here, and actually it's even going to be inhibited. So some aerification holes can be a problem if we don't fill them with sand to the top. So I'm a big proponent from a playability standpoint and from a soil physics standpoint to fill your core aerification holes to the top, to have them last longer and to get the benefit of increased infiltration rates. So capillary rise, again, is water moving up as the soil dries. One thing, though, we oftentimes get a crust on the top or a dry layer. This will help keep moisture in the soil. And also a big problem is in areas, very arid areas in the desert, where we don't have large rains to flush salts through the system. As this capillary rise is the predominant physical movement of water, salts will be deposited on the surface and we get crusty salts, and this can be very damaging to plants because they'll have to work against that high osmotic potential. So some of the wetting patterns, a clay loam is going to wet in an oblong pattern, and a sandy loam is going to wet in an oval pattern, because the gravitational water will move more quickly through the macropores downward, where a clay loam is going to have more micropores. It's going to stop the water and move more laterally. And here's another example of that. We've got a sandy soil, same amount of water placed on 3 different soils. Sandy soil, loam soil, clay soil. So the more micropores in the clay soil are going to take more water to fill. The wetting front will be more shallow. On a sandy soil, water is going to move much faster down through the profile. So simple concept you need to understand to fully understand soil water. So now we get into a fine textured soil over a coarse medium, coarse texture. And if any of you who are familiar with putting greens know that's what a USGA putting green is. We have a finer coarse material with a coarse material below that. Water's pulled down by capillary action. The lower layer will inhibit water passing into it. So once we get to that, what we call the perched water table, water will start to move sideways and not down into the profile. In nature, we can have a coarse A layer over a fine B layer. Water will be pulled down through the coarse layer and then stack up on the clay and move slower through that. So, easy to remember, any boundary layer between 2 layers of dissimilar texture slows the drainage. And we'll show that. So here is a fine texture over a coarse texture like the USGA green, and we see that as the water comes in, it would normally, if it were just the fine material, keep going down, but it stops. It backs up and then fills the entire surface area. And then once the entire surface area is full, almost, there's a little bit here that is still dry, then it busts through and quickly goes through the coarse material. So that's how a USGA green acts, and this is what we say when we want to flush the green, is we want to make sure that we get the nutrients, we get the water all the way filling the entire profile so that we can flush out any toxins or salts or bad stuff that's in the putting green. In most superintendents, it's recommended to do this probably at least once a month to irrigate enough water, and now you have the tools to calculate how much water it takes to flush a USGA putting green, and we will have you do that on the exam, and we'll have you run through that in the lab. So here's another core aerification. They've used rice hulls to fill the core hole. But you can see how dramatically core aerification increases moisture take up in the soil. But if that core hole is sealed off, even just a little bit, it's going to limit that infiltration rate, and we'll get no added benefit. We might get some added benefit from some roots getting in there, but the benefits are much reduced if we don't fill all the way to the top with that coarser material that goes into the core holes. So, a little bit of root anatomy. We've talked about roots in the previous section in the parenchyma formation of the cortex. But root hairs become very important. They're very fragile. They're always reaching out into the soil. These are going to get up into that water around the soil particles, lower the water potential, and bring water in. So what we're doing is we're creating a difference where the air has the lowest water potential and a gradient of water potential from higher to lower as we move from the root tip to the leaf, which allows water to move through the plant from the root to the leaf out into the air, creating a transport system, providing all moisture for turgor pressure, for all the biochemistry in the plants, and also is a mechanism for movement of nutrients from roots to leaves and all throughout the plant. So soil moisture is very, very important to plant health, and you should understand the anatomy of the roots. Root cap, meristem, area of phloem, area of xylem, root hairs, epidermis, cortex, and stele. All of these words are fair game. All of them are good vocabulary words. You should look them up and understand what these words mean. You should also have a good understanding of what hygroscopic water is, what adhesion water is, what bar is and how it converts to psi, what cohesion water is, what gravitational water is, and what field capacity is. So all of these terms should be definitions that you have a working knowledge of. So air is going to be less humid than the soil. As the soil dries, it becomes less moist in relationship to the air, lowering the potential differences until finally permanent wilting point is met, -15 bar. Salt soils add osmotic potential, make it more difficult. The salt pulls against the plant, making it more difficult to move water up into the plant. So probably a reason salty soils, we don't have huge giant trees growing in them, is because the plants can't overcome that matrix potential difference to get to those great heights of a giant sequoia tree. So plants are going to remove water through their roots. They're first going to use the easy water near the surface. As the soil dries, roots will be put down. When the surface layer is re-wet, this absorption shifts back to the surface. So there's a constant wetting and drying cycle. And if you just water 1 inch a day, your turf grass has no incentive to put roots down. So then when you do get a drought situation, you're going to have problems. So George Thompson was one of the best at really drying his plants out in the spring. Greens would be really hard, but he would develop a strong root system that would get him through the summer months of June, July, and August in North Carolina when the plant's not putting down any more deep roots or any roots at all, pretty much. The roots you have on June 1st are going to be much better roots than you have on August 1st in North Carolina. So 2 questions for you. I'm not going to answer them, but we'll talk about them in lab. So how often should you irrigate? And how deep should you irrigate? How often should you irrigate your lawn? So think about those questions and how you should answer them, and we'll have discussion in class on Friday about that. And a little review, you need to be able to do moisture measurements on a weight basis, on a volume basis, and on a soil depth basis. And here's a chart, and you need to go over that and work on that as homework. And also each week figure out how much moisture your plants have each Friday and turn that in on the spreadsheet. And that's it for this section. Take some time. This is a very important section.